Hi everyone, welcome to the February 2nd SIG Apps meeting. I'm Janet Wall. I'm your host today, and together Maciek is going to host with me. Today we have a few announcements. For the upcoming Kubernetes release, a PRR freeze is coming in February 4th, and then enhancement freeze is in February 11th. And then code freeze is coming in March 18th. You can take a look at the link, which I'm going to post in the chat for you to reference. You can take a look at the link to see the detailed release schedule. The second item is that SIG Apps annual report for 2025 is coming, and we're going to publish it soon. And now we're going to go over the discussion topics for today. The first one is from NVIDIA. They're going to introduce the Grove project, give an introduction and overview. So I see we have a hand, Maciek.
Yeah, Janet, didn't you want to also announce the agent sandbox meetings that you set up and people who are already signed up for SIG Apps mailing list, they should have
Right.
received the invite, but just for the record.
Yeah, thank you for the reminder. Yes. For the SIG Apps subproject, agent sandbox, we have a upcoming meetings set up for every other Monday. uh, from 9:30 to 10 p.m. AM PDT on the alternate week of CGAP's meeting. So I've already set up the calendar and sent the invite. If you see the invite on your calendar, that's where it's coming from. We are going to discuss the thank you. We're going to discuss the agenda, the roadmap, and the um, the upcoming features in Agent Sandbox. All right. Think Sanjay, are you going to present?
Yes.
Okay, let me make you a co-host so that you can present. All right, please take it over.
Okay. All right. So let me try to share my screen. Hopefully this works. Is everyone able to see my screen?
Yes, we
Yes.
can see the document.
Okay, perfect. All right. Hi, everyone. I'm Sanjay Chatterjee, and firstly, thank you to the SIG Apps chairs for giving us the opportunity to speak. So today I'm going to be talking about a project called Grove, together with one of my colleagues, Rohan Varma. And so, yeah, we can go over this document. And if you have any questions, we can take it, like, feel free to stop us at any time. So, all right. So let's get started. So what we want to talk about today is basically an introduction about a project called Grove. It's on the GitHub on AI Dynamo. So there's a link, and you can find this. It's an open source project, and so to introduce Grove, so this is basically a Kubernetes API, and it was purpose built for defining AI workloads in a way where the user can provide some declarative, in a declarative way, provide some constraints about how you want to deploy your workload, scale them, and you want things where certain parts of the application will try to coordinate amongst themselves. So you want to make sure that you have a single API where you can describe your entire AI system and AI workload that needs to be deployed on a Kubernetes cluster. So that was the main motivation behind Grove. And with that in mind, I mean, why it makes sense is because AI infrastructure is becoming more complex as we see, and so the need is growing for automated orchestration layers. And Grove is basically an orchestration layer that will try to make sure that your AI workloads, whether it's training, inference, agentic pipelines, all of them can be described in one single unified API. And then you can try to deploy them on Kubernetes cluster and expect consistent performance from these workloads. So that was the motivation behind it. And it was initially motivated by the fact that there are these new kinds of inference applications called disaggregated inference systems. And so to give you a quick introduction about disaggregated inference, I have this diagram. I can show it to you. So in traditional serving models, you can see that an AI inference application can be divided into two stages. One is called the prefill stage, and the other is called the decode stage. The prefill part is basically where you are generating context about your inference. And in the decode part, you're basically creating the tokens, generating the tokens from that context. And so typically, you would find that the prefill and decode would all work within the same, as part of the single model, same workload, and which is all single node. But prefill is a very compute-bound application part, and whereas the decode is more memory-bound. And so when the model started becoming bigger and larger, and then you wanted to shard it across multiple nodes, you would want to somehow disaggregate them into different parts or different components so that you can reduce this, let's say, things like prefill stalls, so that you can process compute-bound parts of the application separately to the memory-bound part of the application. And that's where the disaggregated serving model came up. But the problem is when you're disaggregating the prefills and the decodes, you'll need to actually transfer the context that was generated for that inference application from the prefill to the decode, and that's called the KV cache transfer. And so what this means is that, yes, they can be disaggregated and they can work independently, but at the same time, the KV cache transfers will need to will be done so that the time to first token matters. So you want to make sure that the KV cache transfer happens fast. And so these prefills and decodes, where the KV cache transfer is happening, they need to be co-located on the on high bandwidth networks so that you can get the minimum amount of KV cache transfer latencies. So that was the main motivation about like why we wanted to actually express all these components like prefills and decodes into a API where we can actually describe all of that together. So there are a few key requirements that we realized for any such of these applications is that, like I said, the user should be able to cleanly represent all the components of their AI system. And then users will also need to express scheduling constraints on these task groups. So for example, you want the prefill and decode to be there, and they are different components, but you want them to be gang scheduled at the time so that you don't want to make sure you don't want to be in a situation where only the prefill is scheduled and the decode is not, etc. So these gang scheduling semantics will need to be maintained throughout your application, and you want these different components to have, describe things like minimum replicas and minimum availability constraints. And so those kind of things will need to come in for a hierarchical gang scheduling construct. Then another requirement is that these workloads will need to have some sort of auto scaling capabilities, either independently or as a group. And so you will need to have different dimensions of auto scaling that will need to be built into these applications. And then, like I also mentioned, that to get the optimal performance, you need to have constraints about topology aware placement, so which is going to be critical for optimal performance from these applications. So when we started from these requirements, we wanted to see like if what we can do in Kubernetes and how we can actually address how these requirements in Kubernetes today. So firstly, Kubernetes, I mean, before the workload API came up, Kubernetes lacked any kind of like native support for gang scheduling. And so I think the workload API is a great first step in addressing that. We definitely need to get like native support for gang scheduling into Kubernetes. But I think there is still some gaps that we have actually raised an issue. You can put in a link over here. So there's an issue that we have created on the workload API where some of like the requirements for hierarchical gang scheduling are not yet addressed, but I'm sure they'll be addressed. So this was one of the main features that was lacking in Kubernetes, and we hope that in future workload API is going to satisfy all of our requirements. And then the other part of the requirement was how do we actually express? How do we express all of these constraints? How do we express our requirements for gang scheduling? How do we express how things are brought together in the single application, the different components, how they scale together? And so there were no traditional Kubernetes workloads, like stateful sets or deployments, etc., that could actually handle groups of pods together. They were all meant to, deploy and scale individual pods. And so leader worker set, of course, is the prevailing industry standard, for Kubernetes to orchestrate groups of pods using a leader worker pattern. But LWS was not actually, created with disaggregated inference in mind, or basically having, how to describe like multiple interdependent components and scale them together. And I mean, typically you will find that for people who are trying to do disaggregated inference, having to deploy, multiple LWS resources to coordinate the full system. And finally, I think Kubernetes also lacked like comprehensive support, in terms of the scheduling aspects around topology. I think that was something that is also getting addressed through the workload API, and I think it's a deep, it's a more like a wide topic, and where you want to address this issue of topology aware scheduling. It's not just during like when you want to do the initial placement of workloads, but also during auto scaling, preemption, rolling updates, and so on. And so typical APIs around pod affinity and spread constraints really do not address the core problem about how you actually maintain and manage topology not just during initial deployment, but also like when you're doing operations, etc. So these were the main points that motivated our project called Grove. And so one of the key use cases for Grove has been to like enable these distributed inference frameworks like NVIDIA Dynamo and LLMD, right? So they are the frameworks which are actually running disaggregated inference at scale. And we want to make sure that there is a clean API that we can use in NVIDIA Dynamo, for example, to express the workloads. And so the goals for Grove are basically to ensure like to enable multi-node auto scaling, self-healing, updating, basically core Kubernetes ethos around like operations, making sure that they're able to handle like not just at one pod level, but not just at group of pods level, but also like multiple components in the workloads. Hierarchical gang scheduling is another very important requirement for us and a goal for us. Topology-aware scheduling, of course, like I mentioned, is very critical for optimization, like performance optimization. And then the other thing that I think has been missing in mostly in Kubernetes, because of a lack of like multi-node support, is like how do we manage the startup of these multi-node applications? And it's not just startup of like it's not startup like in the sense that you're creating a pod after another, but after your gang scheduled, you still want to maintain some, startup ordering about how these pods, start up after once you're scheduled on through the nodes. So that is another goal that we have, like making sure that the startup ordering is maintained. And then also we want to ensure that, there is a unified API for all kinds of AI workloads, not just training and inference, agentic pipelines, all of that. And finally, we want to make sure that whatever we are designing with Grove APIs, gets adopted by the Kubernetes community. We are just at V1 Alpha 1 today, but of course, like we are open to like receiving more feedback, understanding how we want to uh, move ahead like in the future. So I think getting feedback from the community is going to be super critical. So that's basically our goals. In terms of, I think understanding more about the user stories, I'll let Rohan, talk a little bit from his perspective on some of the proposals, like how we are actually thinking about Pro.
Yeah, thanks, Sanjay. Before we get to that, though, if there's any questions, we'd love to answer that. Otherwise, we'll get started.
Yeah, there's a question from Kevin.
Yeah, I guess. Sorry. So for the startup ordering for MPI-based workloads, it seems like you're focusing more on inferencing, but you're also kind of mixing and matching some distributed training use cases
Yep.
also. Have you like some of this overlaps with job set also? Like from the SIG apps perspective. So I was curious if you have looked into job set for some of these cases to solve these use cases.
Yeah, definitely. I think so. Like some of the users who use Grove, I guess the thing they like most about it is that they can use it for both training and inference. So instead of like using Jobset and LWS, you can just use Grove. And I guess once I explain the pod design, or sorry, the user API design, it'll make more sense why. Because the core, I guess, value prop, like very core. There's multiple things layered on top of it, but at its core, the core value prop, like Sanjay explained, is being able to express the components of your AI system, whatever it may be, training, inference, agentic, whatever else comes up in the future, with one set of composable primitives, basically. So that if tomorrow some new class of workload comes up with some like new, like, I don't know, like way of being set up, we've very much tried to create Grove's primitives in such a way that you can just compose them and be able to represent your system. And that's why, like in the user stories, we have such a wide range of things, because the goal is really to just have one unified API that you can just map to your problem.
Okay, thank you.
Cool. And that way we don't have to keep like reinventing the wheel, I guess. Like we can be proactive instead of reactive. Any other questions? Okay, cool. Yeah, so let's get into some of the user stories. And as you'll see, they span quite a wide variety of things. And it'll make more sense how we're able to achieve this after I go through the user stories and go into the design. So to start, like the first one, like Sanjay said, was we were motivated by disaggregated LLM inference. So if you're some kind of platform engineer that's deploying disag, you want to be able to have a single resource that can define all your components and manage their life cycles together. So that, and you want that for a few reasons. You want to avoid partial deployments, and you don't want to maintain like manual coordination of all these different resources. And also like things around like updating and like versioning, you kind of want that to be in like one resource so that you can cleanly just keep track of everything. And Grove will allow you to do this, as you'll see once we go through the primitives. There's one core thing called a pod click set that will be designed such that you can contain all your prefill and decode workers within that pod click set, and within that pod click set cleanly describe, okay, I need at least a prefill and a decode to be functional, and I want this many prefills, I want this many decodes, I want them to scale in this way, so on and so forth. As part of that, another user story is you want to have a So the user-facing API design, we'll be going over it soon after the user stories, but it's right below in this doc if you want to get a sneak peek earlier. So in line with what I just described, one thing that you'd want in this DISAG serving case is gang scheduling to prevent GPU deadlocks. But this is also something that you want in other classes of workloads, like training, agentic systems, etc. Typically, you need some set of components to be able to actually serve traffic, and you want to make sure that you're not dedicating resources to it unless you're actually going to be able to do some work. And so in Grove, basically, every component that you specify within a pod click set, you will be able to put a min available on it, which will allow you to gang schedule things and make sure that things are scheduled in an all or nothing way. And as you'll see, you'll be able to put these min available constraints at multiple levels of the hierarchy, which will basically allow you to ensure that, like, if you have a prefill worker that's, say, multi-node, meaning like it requires multiple pods to create one instance, you can say, like, I need 4 of these, or otherwise this prefill instance is not valid. And then you can also say, I need a prefill and a decode, otherwise it's not valid. Going to part 3, like Kevin mentioned, for MPI-based workloads, startup ordering is like very key. Where like typically the way MPI works is you have one pod effectively spawn all the processes on the other pods via SSH. And you, of course, need all the pods to be started and ready and initialized with their SSH before the leader pod, if you will, can spawn processes on them. So it's very important that everything be gang scheduled together, but then ultimately the leader wait for all of its workers to be ready before the leader spawns any processes on it. In Grove, we have a startup dependency mechanism that allows you to say that, like, this component will wait for this other component to actually be ready, and all the pods of that component to be ready before you actually start up, which allows you to be able to basically do this startup-based MPI workload. On that note, you've been hearing me talk a lot about multi-node prefill workers, multi-node decode workers. As models get bigger and bigger, and people still want to run them on, like, say, like H100s or things like that don't necessarily have as much memory compared to, say, like the latest GPUs or latest hardware in general, multi-node workers are becoming more and more important. Also, as we have more scale-up systems like GB200 and NVL72, which give you high bandwidth interconnects between multiple nodes, people are more and more willing to actually deploy on multi-node systems. And one thing that happens here is, before, pod scaling was always kind of a like single unit concept. Obviously, if you have like a multi-node worker, it needs to scale up in the sense that if I have 1 leader and 3 workers, or frankly, like the leader worker pattern is not set. Today, like there's already starting to be more complex systems around like heterogeneous hardware, where they use like different things for prefill and decode, and even different things within decode itself, where it's not just a leader and worker anymore. You just have a set of components that together form a quote unquote like super pod, if you will, that basically is a set of pods that together represents one instance of a worker, and therefore needs to scale as one instance of a worker. So in Grove, we have a primitive called a pod click scaling group that allows you to basically specify a set of components or pod clicks that scale together, meaning that if I have, say, 1 leader and 3 workers to map it to like what LWS does, as you scale that, you'll get 1 leader and 3 workers. But you're not limited to this leader worker set pattern, where if I have like a leader worker and some other third role, I can just put that into my pod click scaling group, and then all those will scale as a unit. This is a little bit more flexible in that sense, and not tying multi-node scaling to leaders and workers. Next piece is network topology replacement. So obviously, if I have these multi-node prefill and decode worker units, I want all the pods within a multi-node prefill unit or all the pods within a multi-node decode unit to be topologically close, because especially for like, well, actually, regardless of inference or training applications, they're going to be doing a lot of communication between them, and that's going to decide your performance, and that's going to decide your cost. So it's very important that if you have a data center set up with certain high bandwidth interconnects in between them, or even within a node, that workers are placed on the most optimal configuration that you can possibly do to save cost. Another thing is, like, even though we're representing all these components within one custom resource, customers often want to actually scale these components independently. So another important thing is that if I have prefill workers and I have decode workers, the way to scale it most performantly is not to just scale in fixed what are called XP/YD ratios, meaning like I don't always necessarily want to maintain 2 prefills to 1 decode. And in general, when you have multiple components in an AI system, even though you want them represented in one resource, because this underlying software is often very fragile around things like if you have different versions of different things, they might like break. And also you want these like gang scheduling constraints, and you want these topology aware constraints, and you want to in general just version them together, which is why you want them in one custom resource. You still want to be able to scale them independently. So this issue is something that we designed for, where basically when you specify all your components in a system, you still retain the ability to specify different auto scaling constraints on each of them. Again, will make more sense once we go through the API design. Then for 2 more cases, basically we're just showcasing how we've designed Grove to basically be, I guess, general, not just inference, not just training. Another use case is people want to use it for like agentic pipeline orchestrations, where maybe you have like multiple models. Here, again, just like we wanted prefill and decode in one system, now you actually want all the different stages of your agentic pipeline in one system, so you can again reason about their versioning and all those pieces and their scaling and coordination in general. And the last one is large-scale training, whether it's pre-training or some kind of like RL training system where there's actually both training and inference. Is you're going to have a lot of components here that you need to be able to reason about, and they all, again, need to be very tightly coordinated with things like gang scheduling and topology awareness. So in general, like, it's not going to cut it to just have like a huge swath of different things, because this software is, again, very fragile. So you do want to be able to reason about it in general. So again, with Grove, as you'll see, you'll be able to just compose a bunch of components, a bunch of pod clicks together into the pod click set, and be able to represent what you have in your system. So in terms of some risks and mitigations, briefly, before we go into the Grove API, hopefully I've primed your interest into wanting to see how we're actually able to achieve a composable set of primitives that allow you to express all this wide range of user stories. But briefly, before that, some risks. So some frameworks like Dynamo, they obviously provide higher level user abstractions via their own like operators and custom resources. In order to be able to leverage Grove for these cases, we would have to integrate with them. Now that's, I guess, more just extra work if we want to be able to expose this to some of these higher level frameworks. And then another, I guess, risk is that Grove really is supposed to be an intent expression layer, as Sanjay said. The goal here is to provide a easy to reason about set of primitives, such that regardless of what kind of AI workload you have or what it evolves into, you can take your system and map it to a set of Kubernetes primitives, basically. And we want to be like future-proof in the sense of we want to come from a first principles approach of AI systems have components that are single node and multi-node. We want to allow you to be able to compose them all. Of course, this means that if we're an intent expression layer that lets you construct your system with Kubernetes primitives and express how you want it to be scheduled, basically, we need something to actually enforce that intent. And so that's where right now we rely on like advanced schedulers like Kai, but in the future, we want to integrate with like workload API and in general upstream, whether it be through like plugins that we write or the community writes, so on and so forth. We need an actual scheduler to be able to express all this intent that people will declare in Grove. So with that said, let's quickly jump into some design details about the user API, and then I'll open it into questions once I explain the core primitives. So the Grove API consists of a user-facing API and a scheduler-facing API. The user API is basically the intent layer I've been discussing, where you are able to describe the components of an AI system and declaratively specify how you want it to be orchestrated, including gang scheduling, topology awareness, auto-scaling, etc. And then the scheduler API, which Sanjay will talk about a little bit after, describes how we try to translate this user-facing API into a scheduler API that hopefully then various schedulers can understand. But to start with, as I mentioned, the core, I guess, philosophy behind the Grove user API is that AI systems have just a bunch of components. They might be single node, they might be multi-node. We don't know how many components will be in an AI system, and we don't know what kind of patterns, whether it's leader worker today or something else tomorrow, are going to come up. And we basically want to provide a set of primitives that can map to basically all of this. So how do we achieve this? Well, to start, the core unit of Grove is something called a pod click. And a pod click you can think of as not exactly like, but similar to something like a deployment, where basically each pod in a pod click, because a pod click can define a number of replicas, has the same template. And the core idea here is that a pod click represents a specific role or a specific component of your AI system. So in the diagram, we've basically shown a multi-node disaggregated system where you have a front end or some kind of router mixed in. You have a prefill worker, you have a decode worker, but really in this case, you'd say that the roles of your system are basically a prefill leader, because this is a multi-node prefill, a prefill worker, a decode leader, a decode worker, and then a front end and a router. And the idea is that each one of these represents their own role within the system. And so what you would do is you would map each of those to a pod click. And of course, now each of these roles has the same template. So that's basic pod click. So you can say that if you were doing traditional, say inference serving, traditional aggregated inference serving, where each instance of a model is just on one node and one pod, you could very easily represent that by just having one pod click for your model worker. And then you could scale it up and down as you normally do. So that's pod click. The next piece is pod click scaling group. Pod click scaling group is what unlocks basically LWS style functionality, but with the flexibility of not being locked into the leader worker pattern. Basically, the idea is that you have these pod clicks that represent all these roles, but some of these pod clicks are actually very tightly coupled into multi-node units that need to scale together. For instance, in the diagram, you have P leader and P worker. Realistically, you need one P leader and three P workers replicas together to be able to actually represent one prefill. So the idea is what you can do is you can say that the pod clicks of P leader and P worker are in a pod click scaling group. And then what happens is if P leader has replicas 1, like in the diagram, and P worker has replicas 3, like in the diagram, and they're in a pod click scaling group, you can then scale the pod click scaling group to say okay, take that from replicas 1 to 2, and it'll get a new unit of 1 leader and 3 workers. Now, the thing is, this is a bit less locked into the leader worker pattern because there's no limit on how many pod clicks can be in a pod click scaling group. So as I was alluding to, there's already systems where it's not just a leader and worker, because you're doing heterogeneous hardware for prefill and decode, and also even within decode. So in those cases, I still have these multi-node units, but actually I have 3 pod clicks that I put in there. And as things get more complicated, I have no idea how things will evolve. But this is basically just future-proof to that, because however your multi-node unit is constructed, you can just compose as many pod clicks you want into a pod click scaling group and proceed from there. And then the last piece is a pod click set. So this is basically a recognition of your AI system has multiple components, and you want to be able to represent all of them in one custom resource. So all of these pod clicks and pod click scaling groups are basically part of a pod click set. And the idea is that the pod click set represents your actual system. So no matter what your system is, you just see okay, my system is made up of this component, this component, this component, this component. You create pod clicks for all of those. If it's a multi-node component, then it'll probably be made of multiple pod clicks within a pod click scaling group. And you put all of that in a PCS, which is a pod click set, which is the top level thing that encompasses your whole system. And the pod click set can also be scaled across, say, regions or something, where you can have I guess multiple deployments of your system across zones. So those are the core 3 primitives. Before I get into some of the things around min available briefly, any questions on understanding this model? Okay, cool. So hopefully now it's clear that this is a set of three core primitives that basically allow you to map whatever components of your system there are to actual Kubernetes primitives. As I mentioned earlier, a key thing that we allow is being able to specify how you want these components to be gang scheduled and scaled. So you can see here in the diagram that all the pod click scaling groups have min available on it. So this is what allows you to say that, like, look, I need at least one prefill, which is because min available is one, and at least one decode, and at least one front-end replica in order to be able to have a functional system. So if you cannot give me that, then do not schedule at all. Additionally, within the pod clicks themselves, I also have min available. So when it's a standalone pod click like front end, what that means is, I guess, just standard. It's like at the top level, I need one front end, I need one prefill, I need one decode. But for pod clicks within the PCSG, we also have min available. So this is telling you that in order for a prefill replica to be schedulable and valid, I need at least one leader and at least two workers. Now, in real life today, most application cases wouldn't have, say, like min available of 2 for P worker when they ask for 3 workers, but the inference frameworks are working very hard to actually enable this kind of scenario, where, like, in reality, if normally you say you need 1 leader and 3 workers, you might be okay with 1 leader and 2 workers. So we're ready for that as well, because we've allowed you to specify min available that's not necessarily equal to, like, replicas. Another thing you can notice is, like, there's replicas on basically everything. So you can choose to scale entire prefill units. You can choose to scale a pod click within a pod click scaling group. You can choose to scale a standalone pod click, or you can choose to scale the entire system across zones. In other words, the core idea is that, like, you can specify whatever intent you want regarding what needs to be gang scheduled, what needs to be scaled. And then the last piece that's not shown here is topology constraints. So we also have topology constraints at each level, where you can say everything in the pod click set needs to be operate within this topology level. Everything within a pod click scaling group replica needs to operate within this level. And putting that all together is how you get basically the Grove user API. So with that said, if there's no questions, we can turn it over to Sanjay to describe how this gets translated into the scheduler API.
Yeah. Right. Thanks, Rohan. All right. So to quickly, talk about the scheduler API, I think what Rohan also mentioned was that Grove is basically an intent expression system. So what that means is that Grove is not trying to do your scheduling, but it's trying to define your constraints for the scheduler. And so what we have done is we've defined a scheduler API, which is called the pod gang. And a pod gang, you can translate your pod clicks and pod click scaling group and the pod click set into one or multiple pod gangs. And these pod gangs can be a set of these pod gangs define the entire constraints of the system. And we want the downstream schedulers to basically take these constraints for scheduling and make sure that they are satisfied. So basically, when you define a minimum functional system, like what Rohan was talking about, we want to make sure that not just during scheduling, but also during rolling updates and scaling, you need to maintain a minimum functional system, and Grove understands that from the main availability from the different parts of your API. And then it will make sure that when your inference application is running, you're not taking any downtime, let's say when you're doing rolling updates and things like that. And this is an extremely important part for us to understand. It's not just a one-to-one mapping of like taking a pod click set or a pod click scaling group and turning it into a pod gang set or a pod gang, but essentially understanding what needs to be gang scheduled at what time is extremely important. And so what the Grove architecture looks like is essentially, I'm not sure. So the Grove architecture basically takes in a pod click set, and that is the external user-facing API. And so the user basically writes a pod click set, and it will contain all the specifications for what goes as front-end pod clicks, or let's say your prefill scaling group and the decode scaling group, and all of that goes into this pod click set API. And then the Grove operator takes that pod click set API from the user and then it'll create a bunch of different custom resources. Things like Rohan mentioned, the pod click and the scaling group, these are all Grove managed custom resources. And it'll also create other kinds of resources such as secrets, HPAs, any kind of services that are required, etc. And then it'll also, the most importantly, it'll generate the pods. And then and the constraints for scheduling those pods is captured into one or more pod gangs. And then these pod gangs are given to something we have some in Grove, which is the retargetable scheduler backend. So today, Grove out of the box, has support for Kai scheduler. But we also want to make sure that we will support workload, the workload object workload API that it's currently coming up in the Kube scheduler, as well as any other custom schedulers that are going to be popular from like either Volcano, others. So this retargetable scheduler backend makes sure that the pod gang constraints can be translated into whatever constructs that the downstream scheduler can use. For example, Kai scheduler uses pod groups, Kube scheduler will use workload API, and so on. And so with these, we can translate our constraints for the scheduler, and then which can be used by the scheduler to do the scheduling and binding of the pods to the nodes. So essentially, I want to, excuse me. So essentially, this is how the Grove operator operates from user specification of a pod click set, and then it'll make sure how to maintain all these specifications over time as you run these applications in production clusters as well. So I think that's basically what we wanted to present about Grove. This is a very short introduction and overview. The repo definitely has more information about user guides and examples and things like that. So I just to give a brief spiel about why we are actually putting this up in SIG Apps, because we believe that SIG Apps is the community forum, right, for consolidating any kind of Kubernetes application requirements. And so I think these are very important applications that we want to support natively in Kubernetes. And so we believe that we're bringing up all these requirements to the community, and SIG Apps gives us a platform to do that. So in that spirit, we want to make sure that Grove can actually have an aggregated AI workload API that others can start using and giving us feedback and also adopt, so that we can figure out what are the current gaps in Kubernetes, what are the future gaps in Kubernetes, and work towards making Kubernetes whole in terms of addressing any such limitations. And so if it makes sense for the SIG Apps charter to add Grove to its charter, I think we'd be happy to explore it. I think that's basically what we had to talk about Grove in this forum. Thank you everyone for the opportunity. If you have any questions, we can take it now. Okay, I'll stop sharing.
Hi, I'm curious. Thanks for the presentation. I'm curious about what's the potential for making changes to the API, for example, because there are some overlapping with job set. If we want to maybe consolidate or consolidate the two projects or make them work together or merge them, is it possible to do that?
Yeah, that's a good question. So yeah, of course, we can try to explore any sort of consolidation of API or anything, but essentially Grove is trying to be the API that can do all kinds of AI workloads, and we will see in terms of what makes sense to consolidate in terms of APIs and see what can be translated easily. There are some requirements in Grove which are very let's say specific to disaggregated inference, which we might see if if it can translate easily, or that'll actually constitute a huge change in job sets, characteristics, etc. So there are lots to be explored in that sense, of course, but I'm open to discussions and things like how we can consolidate that.
Thanks. And another question is about, because for putting things in the upstream, we want to make sure that we make it vendor neutral. So I'm curious about whether there's anything specific in Grove that's specific for NVIDIA.
No. So there's nothing which is NVIDIA specific. It's very generic. The API is generic. It does not say that you have to use GPUs. But of course, like optimizations for GPUs, we can always do, and not just for GPUs, but any kind of hardware optimizations that we want to do is, of course, possible. So yeah, it is a vendor neutral platform and API.
Kevin?
Yeah, so I'm curious if you've taken these ideas to like the leader worker set community, or because I feel like there are definitely examples like from the LLMD side or SG Lang or Grove. They're all kind of doing similar things. And at one point, I guess we were hoping leader worker set would aid here. And I know that I think the leader worker set GitHub repo has some ways they support some of this. Maybe some of it's more like there's like a higher level API that's wrapping leader worker sets. But I'm curious if you've engaged with that community at all on this.
Yeah, for sure. So actually, some of the leader worker set examples are mine. The tier TLM one, I long ago tried to get multi-node Triton plus tier TLM into leader worker set. I wrote a blog about it, eventually fed back. One of the main motivations of Grove initially was some limitations around leader worker set that basically can't be addressed unless, as you mentioned, you build yet another operator on top of it. And basically, there's obviously my specific role within NVIDIA is to work with customers, mainly more on the lower level inference side around like VLM, SGLang, tier 2M, those types of things. And we were finding certain issues when we'd actually try to deploy this with leader worker set with those customers around things like, okay, how do you actually like upgrade them? Or if you want to upgrade them, like both prefill and decode in like one unit, then if you need to represent it all in leader worker set, if you need to represent it all in leader worker set, that leader worker pattern kind of breaks down because now you have prefill leader, prefill worker, decode worker. You can kind of do it, but you can only do it with like fixed prefill decode ratios, and it's kind of like hacky to like put that in. So then like other people were building another operator on top of that, but then that's making it difficult to like put in like your gang scheduling constraints and reason about like how you want to like specify topology. So what we ultimately realized was like, okay, you just need more flexibility in like the intent. That's why we keep harping on like intent. It's like the gap in leader worker set is fundamentally you can't express what you need to. And it was built basically, I mean, it is exactly what it says, right? It's a leader worker set. So it's just kind of locked into that in that sense. So we wanted to take a step back and think about, okay, what actually makes up an AI system? It's just a set of components, single node and multi-node, that needs some orchestration between them. Can we create some set of APIs that is actually general enough to be able to just adapt to all of this? And so like, yeah, like.
And typically, if you'll see that in today's deployments, you'll end up like needing multiple leader worker sets.
Yeah.
For any production AI system, which means that by definition, leader worker set is not enough. So,
yes.
Yeah.
Or it's not enough because of this paradigm shift that people actually like compared to, I guess, web world where like every service was like extremely decoupled. And like, I guess I would say compared to AI workloads, the orchestration and coordination between those is not as much. In this case, the coordination is a lot more when it comes to like training workloads, where all the pieces of a training workload need to be coordinated together. All the pieces of an inference workload need to be coordinated together. All the pieces of agentic workload need to be coordinated together, versioned together, packed together, scheduled together. So I think it's just become clear talking to customers that like people would prefer a model where you can represent it all in one and cleanly express like, okay, these pieces need to be scheduled together. I need as much of this. These pieces should be close together. When I upgrade, these pieces should go down. I shouldn't have any imbalances between them, so on and so forth. Like the whole life cycle of these types of applications, I think requires a level of, I guess, coordination between the components that we haven't seen before. And therefore, the idea is that you need an API that allows you to express that.
I can maybe add a little bit more too, if that's cool.
Sure, yeah, go for it. Yeah.
I would just say that, like, so I'm an early adopter of Kubernetes. Been using it for many, many years now. And Kubernetes was basically built around this paradigm of like pods and nodes. And now what we're seeing at NVIDIA in particular is like racks that connected with like high bandwidth interconnects, and then racks of racks that are going to be connected with high bandwidth interconnects. And so like the abstractions around nodes and pods is like it's growing beyond that, and like we need a way to like, you know, do it all in one place where we can say that this stuff needs to be scheduled together and these are the requirements and constraints. So it's kind of the computing paradigm is changing, I think, and we're trying to figure out how to adapt that with Kubernetes, because we like
and not just
we
at
like
NVIDIA,
it.
right? Like AMD has a scale-up solution now with their like Helios rack. Trainium is like doing a bigger rack, and like
supercomputers, right? It's becoming like supercomputers are a new abstraction instead of nodes. Yeah. Anyways, I'll be quiet now.
For TPUs, I understand a lot of this is taken care of at like the like VM provisioning layer, not necessarily Kubernetes. But of course, open source is operating on Kubernetes now. And if we want to keep it that way, we have to allow people to basically be able to express all this without having to build their own custom stacks, basically. I see some more questions.
Yeah, I think Hiba's been messaging exactly what I'm saying. All this is like, I think the Kubernetes community acknowledges all these problems, yes. And that's why the workload, if you look at the KEPs that are being proposed, I mean, part of the issue is that, I mean, I guess it's good that we have the Grove use case, because like it is kind of hard to support like a gang of leader worker sets without an actual API that people are submitting to. And so I think this is helpful to kind of showcase an API that is kind of covering the basically replicated leader worker sets. and so all these requests, I think we are aware of why, and that's why there's a big effort, especially from the SIG scheduling side, pushing this through, and then trying to add first, you know, phase one is gang scheduling, but topology aware scheduling, there is a feature opened up in the Kubernetes KEPs trying to add this to in 1.36 to get that information. So I would suggest taking a look at all those to kind of make sure that the API that they're proposing satisfies your use cases. But yeah, so just wanted to, in case you weren't seeing the message that Hiba was saying.
No, makes sense. And like I said, like this, we need, ideally, we don't have to use custom schedulers to like enforce the intent that Grove provides, right? And that's why like we're excited if like we can map our APIs to workload API, for example. I think one thing about like, I don't see workload API as filling the same gaps in a way. Like if there's three things, right? There's a layer of actually managing the pods and managing the life cycle of the pods. There's a layer where you specify the intent of how you want things gang scheduled and topology packed and all of those types of things. And then there's a layer that actually enforces that intent. In my head, workload API is very good at that last part of enforcing intent. Now, I understand how you might think that there's some overlap with the intent specification, but at least from my point of view, like the way it's currently shaping up, I wouldn't want to specify my intent in that way, where like I have all these different resources and I need to basically like then like either rely on the controller, for example, LWS, to create the workload under the hood, which then is limiting because then I can't have multiple LWSs necessarily as easily, like create some like joint stuff in the workload. And also I can't like roll things with like in this like topology packed gang scheduling aware way as easily. Like it's kind of like a weird split of like the management lifecycle being, I guess, delegated to the like workload API and like scheduler. It's like a little bit odd in that sense, which is why like with Grove, what we've aimed for is the intent around how things should be gang scheduled and topology packed throughout the entire lifecycle naturally belongs in the thing that's managing the entire lifecycle. And then we want to break it down into a piece that the scheduler can then understand. So like in our view, workload API is more of like the thing that should be able to be like we should be able to translate our scheduling intent to it, and then it can enforce it, as opposed to viewing the workload API as a piece that users directly use to actually express that intent, if that makes sense. So I think the core philosophical discussion here is where that intent layer belongs. Does it belong in that higher level operator that like manages the pods, or does it belong in basically what you're doing with workload API as a like scheduler? Hope that makes sense.
I'm sorry, I have to just say one thing before
Yeah.
I drop because I have another meeting.
Sure.
But actually, I'm very glad that to see Groove, because basically it collects every thought that we were thinking about and we were trying to solve in one place. So this is amazing. And actually, I would love for you all to come and join us in Workload API. Why? Because Group is our, like North Star. Like this is what we are trying to achieve right now. Workload API, what we have right now in Alpha, it's basically like just scratch the surface. But there's a topology aware, there's a life cycle, like scheduling life cycle changes, and the workload API will actually change in the, like in the next release, and we will introduce new APIs. So I would love to see, like the gap, or, like what is missing.
Sure. Yeah.
What is missing, so we can adopt in the workload API. And of course, like your knowledge, because like you have a working
Sure.
a working project. It's not even a POC. So that would be amazing, actually, to have you in the conversation.
Yeah. We'd love to collaborate. Yeah.
Cool. Yeah, and I'm definitely going to come out to more of the meetings and chat about some of the things. One thing to get people thinking about, one problem I'm kind of wrapping my head around is schedule gates, and the fact that you remove them one pod at a time, and there's no way to do atomic schedule gate removals. It may not be a solvable problem, but it's something I'm thinking about. And so if you know anything about that, I'd love to chat.
That's a good point. Yeah, and as we deal more with multi-node cases, I think these are the kind of problems that will come up that will need to be solved natively in Kubernetes.
Cool. Thanks everyone for the presentation. So we're at time. Let's follow up in the Slack messages or in the email. Right. Thanks.
Thanks, everyone.
Thank you.